All right. Hello, everyone. Welcome back to the last session of the day, and in fact, the first talk of the school. It's a pleasure to have Hatem Elshatlawy give us a philosophical entry into the physics project and Ruliology. Hatem has been a long time researcher in the Wolfram physics project, even before the institute has started, and now a research fellow at the institute as well as a PhD researcher at the University of Sydney in Australia. Hatem is basically the philosophical hat of our group, and he has been exploring all sorts of philosophical connections of the WPP, and not only the WPP, but also on mathematics and theology and various other things. In fact, before before his work at the University of Sydney, Hatem spent quite a bit of the. Hatem has studied in various other places, including Aachen, Munich, and so on. He was working at the Center for Mathematical Philosophy in Munich, looking at connections of category theory and philosophy. And he has a very broad range of interest at the intersection of physics, math, and philosophy, and also theology and related subjects. So it's a pleasure to have a grand introduction to the philosophy of WPP and its connection and all sorts of connections of reality, Ruliology, and so on. Welcome, Hatem, and the floor is all yours.
Thanks so much, Xerxes, for the kind introduction. For a second, I thought you're talking about someone else. That's very kind of you. Well, thank you, everyone, for joining. Good day, good afternoon, and of course, a wonderful start to the winter school. Okay, so every time I present this talk, I aim to explore it from a different angle so that I can learn something new and so that it becomes fun for me as well. I'll be presenting a high-level overview introduction to the Wolfram model, the physics project, and I'll cover the core concepts, definitions, and the commonly used terminology. High-level overviews bridge gaps between disciplines, and they provide a meta perspective. And meta perspectives are sort of central to philosophy because they involve stepping back to analyze and reflect on the foundational assumptions, methods, and frameworks of thought. But before discussing any of that, why should anyone care about the philosophy of the physics project, multi-computation, the Ruliat, and all of that? Well, of course, to ask why is to master the how. But of course, also it depends on what your definition of philosophy is. But since its origins, when early humans contemplated existential questions expressed through mythology, rituals, and storytelling, philosophy has always served to define and analyze the fundamental concepts, assumptions, and methods of acquiring knowledge. Like what constitutes knowledge and how it is justified, or the nature of reality and what kinds of entities any model aims to describe. You see, this tool or thing people call philosophy enables us to identify commonalities. It seeks shared principles or patterns across diverse observations or stories, of course, offering a holistic understanding. And of course, to also critically examine the methods, limits, biases, and interpretations. Perhaps also philosophical overviews reduce complex ideas into accessible narratives. And as you all know, there is nothing more powerful than a good story. We're symbolic creatures, and because we're symbolic creatures, we can build symbolic descriptions of relations and events. We can string them together and make stories. And because we make stories, that's what makes us different. I also must highlight that this philosophy, which is inspired by the physics project, is deeply connected to humanity's big questions. It really resonates with age-old questions, and it sort of, as you'll see later in the talk, provides answers to these questions. And notice that I said answers, not the one right answer, because as I'm sure you all know, there isn't a single right answer. There are just answers, and what's right or wrong often depends on what works best for you and, of course, what you can and can't know. You see, when we are part of the system under investigation, in this case, reality, it's really hard not to be part of that. There will always be such ontological opacity. You see, a subsystem cannot observe a totality of which it is part. An eye cannot look at itself. Only through a mirror is this possible. But this isn't really the eye looking at itself, but an image of itself. You see, a mirror always yields a representation, and a representation always has some flexibility of interpretation. There is always an epistemic gap when we split the subject and object, which is always required for knowledge generation. So we cannot really transcend the limitations imposed by the need to separate the world from the knowledge acquiring being, attempting to understanding, much like how an eye cannot see itself without the aid of a mirror or some intermediary representation. You see, this circularity arises because we, observers, are both products of reality and participants in defining the laws and patterns we perceive. Rather than being a flaw, this circularity is actually a fundamental aspect of understanding reality from within the system. And the good thing about meta perspectives, or let's say the beauty of meta perspectives, lies in their ability to extract what's common across diverse sets of observations. Meta-analyzing works by identifying shared patterns and similarities, essentially uncovering what's universal across different stories. And so the commonalities across different sets of observations is really your best shot of what constitutes a description of the objective reality. That's the best we have. So in essence, knowing more about the philosophy of the Wolfram model and the physics project allows us to use it as a tool for bridging disciplines and addressing both practical and existential questions, like why does the universe have specific laws and not others? How do structure and complexity arise from simplicity? What's the role of computation in defining reality? You see, engaging philosophically with these questions not only provide meaning and context to the technical and scientific exploration and discovery, it's also really just fun. So not only we're seeking a foundational understanding, but also interdisciplinary bridges. Okay, so this session is intended to be 2 hours, so please feel free to stop me at any time and ask questions. And I think before we discuss the core ideas of the Wolfram model, let me actually briefly introduce what Ruliology is. Ruliology is a term that we often use. It is also a term that is coined by Stephen Wolfram, which means the pure basic science of what simple rules do and how different rules can lead to diverse and complex behaviors. So if one sets up a system to follow a particular set of rules, what will the system do? Or put another way, how do all those these simple programs out there in the computational universe of possible programs behave? Ruliology is all about studying computational rules and see what their consequences are. Okay, so let's start with an overview of the Wolfram model, focusing on the core concepts, ideas. Okay. Okay, so basically the Wolfram model proposes a computational universe constructed using rewriting systems and evolution rules. The model originates from the idea that the basic building blocks of the universe are fundamentally discrete and are governed by computational rules. A key objective of the physics project is to seek a formulation of fundamental physics within the framework of rewriting systems. But actually, before also saying much about the physics project, let me tell you a little bit about the backstory and just the history. As maybe some of you know, the physics project is just some developed seeds of the NKS, just a new kind of science. Okay, so basically, when Stephen Wolfram was writing a new kind of science, studying the computational paradigm and the computational universe of simple programs, he identified 2 key empirical observations. Okay, the first one is that theoretical science is often based on mathematical models, but there is no reason to believe that's the only kinds of rules studied within the context of human mathematics. It shouldn't somehow be the end of the story. Since computer programs effectively implement general sets of rules, why not use those as a more general basis for doing theoretical science? The second observation is that very often simple programs do complex stuff. It doesn't really matter whether they are elementary cellular automata, Turing machines, combinators, substitution systems, tag systems, you name it. It doesn't matter whether they are based on continuous mathematics, based on constraints, based on numbers, strings, expressions, graphs, or more general kinds of objects. It doesn't also matter whether you start from random or simple initial conditions, operate deterministically or stochastically, operate in 1, 2, 3, or more dimensions, one always sees the same kinds of complex behavior. And it's not complexity that's coming from the external environment or that has been encoded in the details of the initial conditions. Rather, such systems are intrinsic generators of complexity. So back in 2002, when Stephen Wolfram was investigating all of that, he sort of proposed this radical conception of the scientific method, where in effect, rather than starting from the phenomena, then drilling down, you start from the very basic parameters, or let's say a class of possible models, and building up using computation to explicitly calculate what a particular model is going to do. And then you try to make connections between the semantic outcome of the actual, the semantic outcome of the model and the actual phenomena observed in nature. So in a sense, the physics project is a natural and a more general continuation of the ideas. We also know from NKS that pattern matching and substitution is a minimal model for almost everything. You know, the concept of an archetype is just a pattern that manifests itself across time and cultures. And so when I say pattern matching and substitution is a minimal model for almost everything, it's sort of an archetypical structure. Okay, so it sort of really underlies all computational, mathematical, and symbolic systems, right? Whether you have a Turing machine or a cellular automata, where each cell, the color of each cell depends on its neighboring cells. You see, it's all symbolic systems rely on this pattern matching and substitution. Okay, so let's start with the Wolfram model, shall we? Okay, so the Wolfram model sort of really provides a discrete framework in which structures like continuous space-time geometries can emerge as a large-scale limits of a more fundamental discrete systems. The evolution of these discrete structures are governed by rewriting rules applicable to graphs, hypergraphs, or strings. To illustrate this, that's basically a Wolfram model hypergraph, which can be represented abstractly as a finite collection of ordered or unordered relations, which is hyperedges between nodes. Okay. So what this definition says is that a Wolfram model hypergraph is just really a network-like structure defined by nodes and hyperedges, defined by the relations the relations between elements. The hyperedges really represent connections between any subset of nodes. And these connections can be directed or undirected. And I mean directed and undirected. If you see that arrow, this is a directed relation. So the hypergraph sort of captures the relationships in a very flexible and general way. One can then also define the dynamics of this model in terms of hypergraph rewriting rules as follows, which is basically that says a rewriting rule in the Wolfram model really specifies how one part of a hypergraph matching a certain pattern is transformed into another part with a new pattern. It's sort of a fundamental way to evolve and modify the structure of the hypergraph. Okay, and so the Wolfram model is basically a general abstract rewriting system based on the principles of hypergraph rewriting, but it also sort of extends beyond that. It sort of encompasses various rewriting systems, such as string rewriting systems, term rewriting systems, cellular automata, and sort of more computational systems. The Wolfram model sort of provides a flexible framework for exploring computational and physical phenomena. Also note that the sequence in which transformation rules are applied is not predetermined, even in the simplest scenario where the rule is applied to every matching and distinct subhypergraph. The initial selection of which subhypergraph to transform sort of remains open-ended. This multiplicity of choices typically leads to different, non-equivalent sequences of evolving hypergraphs. Hence, the evolution of a given spatial hypergraph is sort of non-deterministic due to the absence of a fixed updating order, or rather the possibility of multiple updating orders. Therefore, we can always treat the Wolfram model as a non-deterministic abstract rewriting system. Okay, and that's just you start from this. These are just some examples. You start from this initial condition, this self loop, and then you define this rewriting rule. And basically, after a few steps, you get that, and you sort of get this very complex object, which sort of answers how complexity arises from very simple systems and rules. Okay, so what else? Okay, so again, so the evolution of any given spatial hypergraph will generically be non-deterministic, as we said, due to this lack of canonical updating order. We can always treat this non-determinism by treating the Wolfram model as sort of an indeterministic, non-deterministic rewriting system. Okay, so let's talk about multi-way systems, which are very, very, in my very humble opinion, these are the most fundamental and interesting objects in this class of models. Okay, so basically, an abstract rewriting system, or actually, let's also say, okay, in general, an abstract rewriting system is a structure consisting of a set A, where each element is sort of called an object, and you have a binary relation referred to as the rewriting relation that specifies how one object can be transformed into another. And of course, a concrete way of also representing the abstract rewriting structure of a Wolfram model system is through the use of a more general combinatorial structure known as, we call it the multi-way rewriting system, which is combinatorically as a directed acyclic graph of states determined by the rewriting rules that sort of generate a potentially infinite multi-way evolution graph, together with, of course, a partial order on the rewriting rule applications and their causal structure. Okay, so that's the definition of a multi-way graph, multi-way system. And basically, okay, so in the case of okay, in the case in the case that future applications of transformation rules in the Wolfram model may have dependencies upon other rule. I'll talk more about the multi-way systems in a second, but before going very deep at multi-way systems, let me actually also mention the causal graphs and all that good stuff. Okay, so basically, let's see. Okay, in the case that future applications of transformation rules in the Wolfram model may have dependencies upon prior rule applications, such that updating event B could only have been applied if event A had previously been applied. Such dependencies may be captured by the causal graph, which is basically a causal graph is a directed acyclic graph in which every vertex corresponds to an application of an update rule, an update event, and in which the directed edge A goes to B exists if and only if the input for event B makes use of hyper edges that were produced by the output of event A. Okay, and so that's a multi-way system, and that's the causal graph of that multi-way system. So far, so good. Okay, so let me introduce you to causal invariance, which is a very interesting property. You see, a multi-way system is said to be causally invariant if for any two paths that start from the same initial condition and evolve according to the system's rules, the resulting causal graphs are isomorphic. Okay, so causal invariance is really defined to be the property, defined as a property of multi-way systems, whereby all possible evolution paths yield causal networks that are eventually isomorphic as directed acyclic graph. Okay, that's also the definition. If anyone is interested in these definitions, you could find them in many of the papers that were published. Okay, so let me also briefly introduce you to branchial graphs, which is these things we use often. Okay, so causal graphs provide one kind of a summary of the evolution of a system. Of course, based on capturing the causal relationships between events. What we call branchial graphs provide another kind of summary based on capturing relationships between states on different branches of a multi-way system. Okay, and whereas causal graphs capture relationships between events and different steps, branchial graphs capture relationships between states on a different branches at a given step. Okay, so branchial graphs effectively show how, let's say, show common ancestry between multi-way states. So let's say vertices A and B are connected by an undirected edge in the branchial graph if and only if they share a common ancestor. Okay, so that's an example. Take this multi-way system. Take the last slice that says ABA, BAA, and these P's, they share a common ancestor, which is that guy over here. Okay, so very interesting also graphs. Okay, so okay, the Wolfram model is really fundamentally a discrete space-time formalism in which the continuum structure of a manifold emerges as the large-scale limit of a discrete causal network, and the causal network is generated in a very natural and algorithmic way from diagrammatic rewriting rules. So we're ultimately trying to develop an explicitly computable and constructivist foundations for physics based upon the space-time, whose parallels to causal set theory, causal dynamical triangulation, spin networks, spin forms, and loop quantum gravity, all that good stuff. Also parallels to constructivism and intuitionism in the foundations and philosophy of mathematics. And just as constructivism is about giving explicit algorithms for constructing mathematical objects, the Wolfram model for physics is all about giving explicit computational processes for constructing physical objects, rather than reasoning abstractly, like saying, let M be a manifold, let S be a space-time, let H be a Hilbert space. Instead, you say, here is an algorithm or a computational procedure that builds me a manifold, a space-time, a Hilbert space. So it is very, very useful indeed to think about space-time and the foundations of physics from discrete and computational terms. Because also in traditional physics, we think of space and time that is something as something that is given. And on top of that, you throw stuff in, for example, matter, and then we hope that matter will interact and stuff happens. And that's how we view reality. But of course, the first thing that one needs to answer if one wants to do physics in a background way, where does space come from? What's the underlying structure of space? And one way to answer is through the rewriting systems. So one could say that at the lowest level, we're trying to build a machine code computational description of life or the universe or reality, you name it, in which everything just consists of a network of atoms of space that is being updated all the time. Okay, so let's talk about multi-way systems. And of course, the concept of multi-computation. Okay, so F1, okay, Stephen has done this blog, I guess, called Multi-Computation as the fourth paradigm for theoretical science. And he says that F1 looks at the history of theoretical science. One can identify three major modeling paradigms that have been developed over the course of scientific history. Each of them, of course, leading to huge progress. Okay, the first one, originating in antiquity, one might call the structural paradigm, and its key idea is to think of things as being constructed from some kind of sample to describe elements, and then to use something like logical reasoning to work out what will happen with them. Then there is the mathematical, the mathematical equations, which rely on formulas to describe phenomena. Many would say that modern exact science was launched in the 1600s with the introduction of what we can call the mathematical paradigm. And basically, the idea that things can be described by mathematical equations and that their behavior can be determined by finding solutions to these equations. And I guess for hundreds of years, basically it was the state of the art in theoretical science, this mathematical paradigm. And I think a lot of course, a lot of progress was made using it. And then of course, we in sort of in the 1980s, there was also some progress based on a new idea, the idea of using simple programs rather than mathematical equations as the basis for models of things in nature and elsewhere. And part of what this achieves is to generalize beyond traditional mathematics. Because in the mathematical paradigm, one imagines having a mathematical equation and then separately somehow solving it. But if one has a program, a computational program, one can imagine just directly taking it and running it to find out what it does. And this is basically the essence of the computational paradigm, to define a model using computational rules and then explicitly be able to run these rules to work out their consequences. So in the ordinary computational paradigm, the typical setup is to have a system that evolves in a series of steps by repeatedly applying some particular rule, okay? But our models, for some rules, they are not deterministic, okay? That means that multiple choices of substitutions are possible, which yield different results. Usually, we just pick one possibility and ignore the rest. But the multi-way system explores all possible substitutions at once, and sort of it provides a kind of a new kind of understanding. So a key idea of these models is to consider all those possible threads of history and to represent these in a single object that we call a multi-way graph. Okay. Consider this as an example, the system defined by the string rewriting rules. A goes to BBB and BB goes to an A. Okay. Okay. What happens that starting from A, the next state has to be BBB. But now there are two possible ways to apply the rules, right? One generating AB and the other generating BA. And if we trace both possibilities, we get this multi-way system. And it's not really difficult to construct multi-way system models. I mean, there are multi-way Turing machines. There are multi-way systems based on rewriting not only strings, but also trees, graphs, hypergraphs. There's also multi-way systems that is based on numbers, all kinds of multi-way systems. It's really, it's sort of the start of a new paradigm of modeling using multi-computation. Okay, so okay, so basically at the core of our physics project is actually a new paradigm that goes beyond the computational one. A fourth paradigm that we call the multi-computational paradigm. It really transcends physics and applies quite generally as a foundation for a new and broadly applicable methodology for making models in theoretical science. And it's really important to emphasize that the multi-computational paradigm is at its core not about particular histories, but about the evolution of all possible histories. And in most cases, it won't actually have things to say about particular histories, but instead what it will describe is what an observer sampling the whole multi-computational process will perceive. Okay. You see, okay, so yeah, okay. If you really integrate the observer in this multi-computational paradigm, which basically what the observer does is that it coarse-grains the vast computational complexity, right, into coherent, perceivable physical laws. Let's talk about that in a second. Okay, we will come to that. Let's talk about the rule yet. Okay, so now instead of looking at all possible ways a given rule can update these rewriting systems, like what the multi-way system does, imagine the structure of spaces created by applying all possible rules. Instead of just forming a multi-way graph, so a multi-way graph does all possible updates with a given rule. Okay, but imagine applying all possible rules in all possible ways. for a given system. We get what we call the Rulial multi-way system, which is basically the Rulial multi-way graph. Not only does all possible updates, but all possible rules and all possible updates for a given system. Okay, and so that's a multi-way system, a Rulial multi-way system for Turing machines with different S and Ks, number of states and colors. You get these guys over here, and of course we get this guy. Okay, so basically, this construction allows us to really think about the notion of Rulial space, the space of all possible rewriting rules of a given structure. By applying all possible rules and all possible updates, we get what we call the Ruliad, right? You're just really applying all possible rewriting rules and all possible updates, okay? As simple as that. It's really sort of the ultimate limit of all Rulial multi-way systems. And it traces out the entangled consequences of progressively applying all possible computational rules. You see the definition. I think Stephen defines the Ruliad as the entangled limit of all computation, I guess, something along these lines. And so the concept here is just to use not just all rules of a given form, but all possible rules, and to apply these rules to all possible initial conditions, and to run the rules for an infinite number of steps. Essentially, really, the Ruliad involves taking the infinite limits of all possible rules, all possible initial conditions, and all possible steps. It's sort of really the entangled limit of everything. Okay, I remember. That is computationally possible, right? So it's the result of following all possible computational rules in all possible ways. That's what the Ruliad. Okay, of course, this image can be considered as sort of a rough, finite approximation of the real Ruliad, right? The complete, of course, Ruliad encompasses exploration of infinite limits across all conceivable rules, initial conditions, and steps. Okay, and of course, I have to mention the nodes and edges are not really specific to any single entity. Nodes can represent different entities, such as hypergraph string rewriting rules, Celer automata, you name it. And okay, that's the conceptual definition of the Ruliad, or let's say a computational definition of the Ruliad. Okay, what this definition really says is that the Ruliad is sort of a meta-structural framework encompassing all possible computational or rule-based systems. It's sort of capable of describing any conceivable universe or mathematical structure. It sort of serves as a theoretical domain where the boundaries between representation and reality mix up, enabling sort of the exploration of every computational eventuality, acting as sort of a foundation for multi-computation. The Ruliad really represents the complete collection of all computational rules and their outcome. Within this, of course, infinite construct, every possible physical or mathematical system can be situated. I'll tell you in a second more details about that. However, what's observable or meaningful within the Ruliad is determined by sort of the specific constraints and perspectives of an observer embedded in it, right? This makes the Ruliad both a universal pre-physical framework and a tool for identifying the exact computational rules that align with our perceived reality. It sort of really transcends the dichotomy between map and territory, right? Unifying representation and existence into a single conceptual entity, which I find very fascinating. Okay, so one of the remarkable facts of the Ruliad is that it's in some sense the sort of ultimate necessary formal object. A formal object whose structure is sort of an unavoidable consequence of the very notion of formalization, right? Yes, it can be coordinatized in many ways and sampled in many different other ways, but ultimately there is just one Ruliad. Yeah, okay. Perhaps also one could ask how to enumerate all possible rules. But we can also, here one can use the principle of computational equivalence that tells us whatever basis we use, what comes out will eventually be effectively equivalent. Okay. Okay, so here are some Rulian multi-way systems. I like these guys. These just look nice. I thought I will just add them. A Rulian, okay, that's a two-state, two-color Turing machine, Rulian multi-way system. And that's another one made from hypergraphs of the physics project, right? And that's another one with, based on numbers and all kind of Rulian multi-way systems, really. Of course, also I have to say the pictures can be thought of as sort of finite approximations of the Ruliad. Okay. Let's see. Okay, now I think let's here's another definition of what Ruliology is now since we introduced the Ruliad. Okay, so Ruliology, one could think of it as really the systematic exploration of computational rules and their diverse manifestations within the computational universe or within computational systems. It examines sort of the vast rule space to understand how different combinations of rules can give rise to complex behaviors, structures, and even entire computational universes. By sort of transcending traditional boundaries, Ruliology really seeks to uncover the foundational principles that govern all possible computations. So at its core, Ruliology is just really an attempt to map and understand the landscape of the Ruliad, the totality of all conceivable rules executed in every possible ways, right? In all possible ways. It sort of investigates how individual rules interact with states, leading to transformations that shape intricate patterns and behaviors. Fundamentally, really, just Ruliology is the study of the properties, structures, and implications of the Ruliad. Okay. Okay, so I'll give you a very brief introduction of how to think about this mathematically. If anything, this should get you excited for Xerxes' talk. Please make sure you attend this one. But okay, so how to think about the Ruliad mathematically? Okay, okay, we like to think of this as sort of a computational realization of the Grothendieck's hypothesis, which is basically Grothendieck's hypothesis or homotopy hypothesis states that infinity group points are spaces. Okay, and the question I mentioned before, that is, if one wants to do physics in a background independent way, one has to answer, where does space come from? What's the underlying structure of space? Okay, and one way to answer that is through the rewriting systems. So actually, mathematicians have been discussing that in the foundations for a very, very long time. And mathematicians think of spaces as decomposition of points. And then you can think of path between those points. Then you can think of path between path and path between path between path, and so on. There is some notion of building this infinite tower. And questions like these, in part, motivated the Grothendieck's hypothesis, which sort of gives a recipe for showing how spatial structures emerge from an infinite tower of path between path. And so the construction, the constructions in the Wolfram model, multi-way systems, sort of actually provide a concrete realization of this hypothesis. Okay, deriving mathematical spaces from path between path. Okay, of course we can consider multi-way systems as types, the states of the multi-way systems as terms, and the rules of the multi-way systems as type constructors. Path are then proofs, homotopes between path are proofs of proofs, and so on. You see, multi-way rules correspond to type constructors, and completion rules correspond to homotopes. Of course, more generally, we can think of homotopy as maps of maps with cells between them. Okay, that's a thing, or that's another representation. Okay, so a point in a topological space is a thing. A path is a process. A homotopy between path is a meta process, and you can think of this. Okay, so how does this work? Okay, we have this lovely multi-way evolution graph. Okay, that is basically it corresponds to the evolution of this non-deterministic string substitution system. A goes to AB, starting from the AA initial condition. Okay, okay, and every path in this multi-way evolution graph sort of corresponds to a proof of a proposition. You see, saying, okay, I have a path that takes me from here to there, is sort of a proof, right? If I constructed this path, it sort of proves this proposition that there is a path between this and that. But the thing is, I can have multiple paths that lead to the same point, starting from the same other point, right? And here one can think of the notion of equality. Are these two paths equivalent? Okay, and a key feature of homotopy type theory is actually the ability to describe proofs of equivalences between proofs in terms of homotopies between paths. Okay, so a complete realization of a homotopy map between paths can be given by simply introducing a bidirectional edges mapping vertices on one path to the corresponding vertices on the other path and back again. And so you get this idea, right? It can go forever. You can build this infinite tower. And so the sort of the grand overview is that the Wolfram model really provides a computational realization of pre-geometric structures in physics and mathematical and the mathematical framework of homotopy type theory provides the formal foundation for these structures. Please go to Xerxes' talk to know more about all this good stuff. All right, let's discuss the observer, shall we? All right, so the Ruliology contains everything in it. Let's say everything that is computationally possible. And when I say the Ruliology contains everything in it, I mean that very conceptually. Okay. So one question is actually, why then do we have the perception of the universe, or that the universe has specific laws and that definite things happen in it? You see, the world seems to us the way it does because we are the observers we are, right? But ultimately, what's an observer? And can we make a model, or sort of a more general model of one? As now we have general models like Turing machines for computational systems. You see, in the past, it was usually possible to do theoretical science without really explicitly discussing the observer. Even in traditional physics, the observer has often been considered a passive entity, sort of watching the universe. However, perspectives like quantum mechanics hint at the observer's active role in shaping outcomes. So actually, to say anything useful or to say anything about what happens requires really knowing about the observer. And it turns out that our limitations as observers are, in a sense, what give us many of the most fundamental scientific laws that we perceive. You see, a century ago, there was already some indications of the importance of observers in physics, with like coarse graining in statistical mechanics, choice of reference frames in general relativity, and measurement processes in quantum mechanics. But what we're really calling an observer, what we're really calling observer theory, should be much more definite and much more general and formal, sort of a coherent theory of observers that can be applied to let us derive conclusions in a whole range of different areas. So in general, what an observer does is really to take the raw complexity of the world and reduce it in such a way that conclusions can be made from it. And one can think of there being a certain fundamental duality between computation and observation. The process of computation has the effect of generating new outcomes, while the process of observation has the effect of reducing outcomes by equivalencing different ones together. So computation theory gives us a way to describe possible processes of computation. And the goal of what we're calling observer theory is to give us sort of a similar way to describe possible processes of observation. So what an observer does, what an observer ultimately does is to take in an input from a large set and sort of return an output from a much smaller set. It's sort of a concept, again, that's appeared in many different fields under many different names, right? It's sort of a contractive mapping, a reduction to canonical form, a classifier, a forgetful functor, compression, projection, you name it. The list goes forever, I guess. So what's fundamentally going on whenever we use a sensor or a measuring device, or for that matter, our human senses, we extract statistics fed to models and describe things symbolically, say in human language. Thus, the observer, human or otherwise, acts as a kind of prism or a transducer, converting a potentially infinite spectrum of data into a finite package capable of being processed. You see, why is this? Why is this important? Because physics is highly observer dependent, right? And so understanding more about the observers really is sort of fundamental in many ways. Okay, so actually let's take a basic example, like this gas sensor or gas pressure sensor, okay, based on a piston. Okay, within the gas, molecules move around in a very complicated and random ways, okay, hitting the piston in all kinds of configurations. But to the piston, or the piston sort of reduces out all those details, right? Just of really responding just to the aggregate force of the molecules, the same one of which can be realized in potentially many ways, infinite many ways. And the main point is that we can describe what's going on more formally by saying that observations by the piston identify all the different detailed configurations of molecules. And so basically preserving only information about the aggregate force, forgetting the finer details, right? Okay, the same idea can also be given slightly different interpretations. Okay, so in statistics, in statistical physics, observers have, as just described, they have the effect of averaging over many particles or other degrees of freedom, right? In general relativity, they are averaging over space-time regions and forgetting those details having to do with coordinate transformations. In quantum mechanics, they are basically averaging over many quantum histories, right? In mathematics, the same statements are stated differently in terms of the underlying axioms. I think an intuitive explanation of a more formal example of equivalencing, I think, can be given in terms of coarse graining procedures in statistical mechanics. Specifically, in classical statistical mechanics, the number of microstates for a given system is uncountably infinite, since the positions and momenta of particles generally take place and take values in real numbers, right? Therefore, in order to be able to define quantities such as the omega in the Boltzmann formula, namely the number of microstates that are consistent with a given macro state, right? It is very important, it is necessary to coarse grain these microstates essentially by grouping them together into equivalence classes, thereby sort of obtaining a countable set of states. And in order to define such an equivalence class, one defines two particles I and j as being equivalent, which in this particular case means observationally identical, if the respective positions and momenta are sort of nearby in value, right? So coarse graining is the thing. Okay, and the crucial sort of feature seems to be that observers is always ultimately some kind of a finite mind that takes all the complexity of the world and extracts from it just certain summary features that are relevant to the decisions it has to make. Observers like us have two basic characteristics. First, they are computationally bounded, and second, they are persistent in time. Computational boundedness is essentially the statement that the region of space and time, or the region of space observers occupy is limited. That means we can't really expect to reverse engineer computationally reducible processes that are going on underneath. And in some sense, everything then boils down to, everything then becomes about the interplay between the underlying computational irreducibility and our nature as computationally bounded observers. Okay, so the Wolfram model really takes the perspective that an observer has to be part of the underlying multi-way system, possibly as a subgraph spread across branches. And this view, measurement is really the process of the observer conflating parallel threads of multi-way history with a single evolution, leading sort of to the unique sequential thread of time. And furthermore, the notion of causal invariance, which can be thought of as being associated with path of history that diverge, eventually converging again, is sort of what really guarantees a coherent eventual consistency. And since the rule yard contains path corresponding to all possible rules, it's basically unavoidable that it will also contain what's needed to undo whatever divergence occurs, right? So for every rules, there is the inverse of these rules. All rules, by definition, means rules and their inverses. And so because of causal invariance, the laws of physics are invariant of any frame of reference. Though to realize the laws, one has to set up a system within a given reference frame. Hence, anything's physically observable, it's going to be in a subjective setting. From the subjective setting, when we infer anything objective, it's relative objectivism. So any given observer is interpreting what they see in terms of a description language, which sort of causes them to attribute certain rules to be the rules of the universe. One has to choose what kind of system one is working with, and it's almost impossible to state a law without those choices. Once we make those choices, we are already in a constructive domain. So yeah, if one sets up some particular computational system or a mathematical theory, there will always be choices to be made, right? And our most important feature as observers, that we are bounded, right? The way we parse the universe involves doing an amount of computation that's absolutely tiny compared to the computation going on in the universe. We really just sample a tiny part of what's really going on underneath, and we aggregate many details, right, to get to the summary that represents our perception of the universe. Yeah, recall this example. This example of molecules, right, and the molecules bounce around, right, in a complicated pattern that depends on their detailed properties. But an observer like us doesn't really trace this whole pattern. Instead, we only observe certain coarse-grained features like pressure and temperature. And so in this sense, really, everything then boils down to how an observer chooses or samples the space in which they are located. And a different kind of observer sampling and perhaps parsing the systems differently could in principle identify different features corresponding to different laws of physics. So what's an observer? In the end, the rule yard involves infinite rules, infinite initial conditions, and infinite time. But any way of sampling the rule yard effectively involves making particular choices about how we take those infinite limits. And what's pretty much that's sort of pretty much like the fact as entities embedded within the rule yard, we have to make particular choices about how to sample the rule yard. One can imagine an observer very different from us, say some kind of alien intelligence, who would have different, who would sample different aspects of the rule yard and thus deduce totally different laws. at the end, the observer is just really an equivalencing machine. One can think of it that way. Okay, so second order cybernetics. This is just a very small note that I have to make. You see, second order cybernetics is really based on the idea that no science is possible from a view from nowhere, right? One can view reality, one has to view reality from a standpoint. So one has to consider a standpoint or sort of a perspective or a frame of reference from which the universe is viewed. Without it, without the viewer, there is no view, right? The Ruliology as it stands is abstractly defined as a view from nowhere, a totality. And to carry out scientific exploration in the Ruliology, we must include a system, an observer capable of sampling the space. And we sort of define the Ruliology as the result of following all possible computational rules in all possible ways, right? This is more in line with the second order cybernetics approach. But we must also ask, who's following the results? Who's the observer in this case? And who models that observer? From the outside, the Ruliology is simply understood as the totality of all possible computations. However, from the point of view of any of its part, which of course satisfy the criteria of computational boundedness and persistence, any part of the Ruliology qualified by the boundedness and persistence is potentially an observer of its complement within sort of a specified horizon, which would again depend on its sort of computational boundedness. So the computational or the computations performed by this localized observer realize measurements in this universe. Hence, sort of from the perspective of the second order cybernetics, the object of interest may not be the Ruliology itself, but rather the power set or sort of appropriate categorical generalization of a power set of the Ruliology that encapsulates the observer or encapsulates observers and their interactions. As previously explained, in this sense, everything then boils down to how an observer chooses, samples the space in which they are located, so that their properties are of the essence, which sort of reveals the Wolfram model as sort of a second order cybernetic system. Okay, let's limits of Ruliology. All right, so the limits of Ruliology, right? The impossibility of seeing the Ruliology from the outside. I'd like to start from actually. I'd like to start with a quote from Whitehead. Philosophy is an attempt to express the infinity of the universe in terms of the limitations of the language, right? And yeah, if philosophy is an attempt to express the infinity of the universe in terms of the limitations of a language, Ruliology is likewise an attempt to sort of describe the infinity and the somewhat less limited framework of the representations of computationally bounded observers that are embedded within it, right? So the Wolfram model really depends on coarse graining over path in order to model the observed physics. The coarse graining is, of course, relationally linked to specific observers or classes of observers. And this sort of introduces a limit, since any Ruliadic properties that we can speak of or that we can speak about are, of course, from the point of view of a member of such a class of observers. We can model other observers by changing the properties defining the observer class. But even this is itself generated from our own perspective, and so it will also inherit any associated limitations. Of course, the Ruliology is not something that we could ever directly observe or epistemologically point at. Nor it is presented in such a way, right? It is an abstract entity. And however, in as much as it is abstract, it exists as a representation in the mind of an agent, and so again inherits the limitations, right? Along these lines, a complaint that has been leveled against the Wolfram model that is incapable of making predictions. But that again really entirely misses the point, which is that the Ruliad is home for physical theories. It is the ground, right? A fundamental theory that is this fundamental cannot possibly be expected to make direct predictions of the sort that the critics clearly desire, right? But what it can do is locate them in a web of theories, and moreover, it can suggest entirely new kinds of theory that would then themselves make predictions when sort of properly worked out in the manner appropriate for less fundamental approaches. The task of physics, indeed, is to figure out where in the Ruliad we are located. Ruliology is not then a replacement for physics, but it's a way of making sense of it. What we have described is done not a theory of physics in the normal, ordinary sense. It's a pre-physical framework for any possible theory of physics and should not be analyzed or critiqued in the same way or in the same terms as orthodox physical theories. I think I'll stop here. I'm glad I made it in 1 hour. This talk, I'll ask if you guys have any questions. It's almost midnight my time, so please feel free to ask any questions.
Maybe one question, kind of a funny question. So usually when you try to kind of define some objects which encompass all objects and so on, there are some paradoxes arising. Have you been thinking about, or have you thought about any paradoxes, like some similar to set of sets or something like this? Are there some obvious paradoxes?
I'm very sorry, Pavel, but I was having a hard time to hear you. Your voice is a bit too mushy. Can you repeat the question and maybe come closer to the microphone? I can't hear you. Sorry about that. Maybe you can type it down in the chat if it's easier, but take your time. It's all good, no worries. Yes, of course, we can define. Have you thought about paradoxes similar to sets of sets? It's an interesting question. Not really, but I mean, it's not really paradoxical, the concept of the Ruliad, right? It's just really sort of the ultimate formalization, right? That's the ultimate thing you get from the very notion of formalization. It's if you think of any paradoxes, please let me know. So far, I haven't really found any paradoxical issues or contradictions within the Ruliad, except, of course, other than, as I try to explain, it sort of inherits the same limitations because it exists in the mind of an agent, and any agent is computationally bounded. But no, it's not really paradoxical. Neither it has any contradictions. But great question. Thank you for asking. Shreda, yes, of course, you can define the notion of symmetry for these hypergraphs. I'm sure Carlos will speak much on this. But yeah, of course you can do. Wonderful. Any other questions, guys? I hope this was sort of a high-level overview summary of what this is. Of course, my amazing colleagues will speak in much more details about all these kind of things, but it sort of was laying the ground for all possible things. High-level overviews are quite important when it comes to these to these things. Okay, Jacopo, from my understanding. It's a very interesting question. But of course, I mean, it depends on how you sample. Again, you know, most of these fundamental laws are really a direct. It's sort of not only what exists, but how we see it, right? So it's we participate in the act of creation as sort of a second creators, and so different samplings would of course yield different inaccurate. But again, you know, the thing about meta perspectives or meta analyzing is that you're really trying to extract what's common across different sets of observations, right? Okay, James. So the question was if the Ruliad would include less accurate theories like Newtonian mechanics as broader course screenings, would it also include wrong theories? Or can it offer an understanding of how we would define a theory of an accurate? And is there any example of how a very simple physical theory can emerge as well? I mean, the whole idea of course screening, that's how we do things, right? It's Stephen says how a branching brain perceive a branching universe. So things happen in a very complicated way, and we can't really keep track of everything that's happening. Our minds are just really finite minds, right? We take in all the complexity that's happening, and our minds automatically does that it simplifies it in a very simple way. So we do course screenings all the time. And again, about you see the meta perspectives or the multi-computational thinking. Well, actually, to use multi-computation is to think in a meta level, because again, you know, multi-computation is about seeing how or seeing all possible evolution histories of something, and then you would include how an observer would sample all these possible evolution histories, right? And so you're really extracting it. Okay, to have sort of an accurate course screening, you have to extract what's really common across all these things. But what's universal in these? Because again, that's really your best. Your best thing of your best shot of knowing what really constitutes sort of an objective thing, right? Independent of any of that. But yeah, basically seeing how something evolve in a multi way, so to speak, and how an observer samples these. That's how we get these descriptions. I hope that answers your question. You're muted if you're saying something.
Sort of, but I'll let you go ahead with the presentation. Maybe we can discuss during the school.
Come again, sorry, say again.
I said you sort of answered my question, but maybe not as satisfactory as I was expecting, but maybe we can discuss during the school.
I see, absolutely. Well, if anyone has any input for Jacopo, please, you know, there's Xerxes, there is Nick, there is Carlos, there is James, I guess. If anyone wants to add to that, there's Dugan as well. Please feel free to add in your input, guys. Okay. You guys can also just unmute yourselves and ask questions. But if the chat is fine for you, it's also okay. Okay, following up on Jacob's question, we sometimes work with effective Hamiltonians, effective field theories, which are valid at the scales of observations being made. When the observer of the Ruliad is being talked about, are there any scale-dependent observations allowed, or just the true fundamental theory? Is the theory of the as the fundamental theory is the only theory the observer observes? Not really. Well, the thing is, it's a very good question for sure. But you see, I think it's sort of a metaphysical question, and it's okay. You see, evolution has sort of granted us an ability to describe and perceive the world, right? Yet this ability is very constrained, where we're forced to experience a universe of many scales through the lens of just one, our own. And for this reason, I guess, why I said it's metaphysics, because metaphysics serves as the foundational framework, or sort of the hidden assumptions are often shaped by our limitations as observers, right? Yeah, where we can only sample a tiny fragment of the universe complexity, and we aggregate or we co-screen what we perceive into simplified descriptions, right? Again, this means that our understanding depends not only on what exists, but also how we choose to observe it. Good question. I'm not sure if that answers your question as well, but yeah, well, I mean, it's also, you see, you get also, just like we were able to co-screen this gas example I gave, right? The molecules bounce around in a very complicated pattern. We're not able to trace the trajectory of every particle, but when we aggregate, there is some sort of high-level macroscopic phenomena that we get to observe as well. That's sort of it tells us one or two things about reality. There's nothing wrong or bad with co-screening. That's just really what we are. I mean, it's fundamentally what we do. I'm not suggesting that it's how we can get. It's by default, as a consequence, we get these laws because we co-screen. So again, if anyone has a better answer, please unmute and ask. Say that. Muhammad Sadiq, please go ahead.
So thank you for the presentation, first of all. So you said that that the Ruliology should not be thought of in the way like orthodox physicist should think, should judge or think. So one of the questions that has been, sort of the main focus on physics recently, which is the unified theory of physics or things of that sort. And I remember when the Wolfram project came out, I think that was a few years ago. I was in my undergrad, and it seemed hey, Stephen Wolfram came up with the unified theory of everything. And of course, I didn't have much knowledge to understand what was going on. I read through the couple of the articles then, but it does seem to me now the Ruliology is sort of saying the theory of everything is combining all the theories that we already have and all the theories that we already can come up with, which seems like a sound philosophical argument, but not a very practical argument. So in terms of computations, is there any way that the Ruliology or the Wolfram project can actually, in a way, actually push a limit of an existing physical model or something like this?
Very good question, and very nicely put, very nicely said. Of course, I think everyone would agree here who works here. We hate how the physics project is marketed, right? Of course, it's not a project to find a fundamental theory of everything. It's sort of the line of thinking is sort of a unified or a meta sort of thinking, right? It's as you said, it's a web. It's sort of any theory can be situated and located within this Ruliology. It's sort of the model or the new paradigm that's the new edge that it gives, right? The way of thinking about these, and of course it gives you an edge to make more theories that are observer centric, because you can't really say anything useful without really discussing the observer, right? We tend to just really neglect the observer as if it's nothing in these models, in many models, but to actually consider the observer within a system. As I said, we're really product of reality, and we also get to participate in how we see it, you see. And so there is this circularity, which is sort of, people think it is a flaw, but rather it is really how we would understand, how we would have an understanding of a system that you are within that system. So just really it sort of opens new doors. Again, to really invest in the future, you have to acquire knowledge now. How this knowledge would be practical in the future, it's an open question. I'm sure my amazing colleagues here have probably better answers to your question, but it's just really it's abstract, yeah, it's an abstract conceptual thing, yet it's so pleasing and fulfilling, and it can be applied quite to many new areas. I mean, Stephen and the Wolfram Institute Research Fellows, perhaps Nick and James can speak a bunch about this. They have been applying this multi-computational tools to new fields like biology, like machine learning, like economics, many other things. So it does sort of provide a new insight. Yet itself, I can't, the concept itself, like I can't apply the Ruliad to, let's say quantum field theory, or I don't know, like to a certain aspect of this or that, right? But the thinking I can definitely use as a new tool to approach a new thing. And and I mean, it's mathematically very pleasing, and there's so many connections to pure category theory, higher category theory, homotopy type theory. It's again, it's sort of a computational realization, but it's not the Ruliad. The Ruliad is sort of a concept, right? But we're not really. It's the multi-computational tools is the edge, is the tools that we have developed and we're developing, and the thing that we're sort of working with and developing. So, but yeah, good question. All of the questions are really wonderful. Thank you. Yeah, please, guys, ask more questions. Or
I have sort of a provocation, like, then, like, is there any way we can understand among all of the infinite possible observers that could exist, why are we the kind of observers we are?
we're just product of reality, right? I don't know why you should. It just happens to be the case. Any observer is just really yeah. Well, you can of course make a very minimal model of observers, right? You can also just use the same level of meta sort of analyzing what observers are, but there's of course there's some basic components of a minimal universal observer model. It has to have a sensing mechanism, just the perception, and many others like interpretation, action, adaptation, prediction, right? And of course boundary definitions. Once you have this minimal model of observers, you could apply it to things like, is the electron an observer, right? Is X an observer? And then you could know what's out there, basically. Once we have a more general model of observers, you could ask, is this an observer, right? And then you could have classes of different observers, what they see. But yeah, I guess you have to have sort of a universal minimal model to see what can be an observer. Any other questions, guys? Please take your time. No worries. We can stay here a bit more if needed. If you don't have any other questions.
Well, last call. If any more questions. If not, then let's thank Hatem for this lovely talk. And we can, and certainly feel free to continue this discussion on Discord, on the philosophy channel or any other, maybe wherever you, depending on the nature of your question. Feel free to put these questions there to continue the discussion, and let's get back to project work. I'll be calling some of you for your project meetings, and see you soon then.
Wonderful. Thanks so much, everyone.
Yes. Thank you.
discussions. Thank you, Xerxes. Ciao, ciao.